Assalamu alaikum viewers. Please like, share and subscribe this channel. Links of PDF files used in this video are given in the description. So today's lecture is part 4 of the lecture series of kinetics and mechanisms of coordination complexes. And in this particular lecture, we will discuss about labile and inert complexes. So in the previous lectures, we have discussed about stability, and it has been proved that stability is of two types: thermodynamic stability and kinetic stability. But when we are using stability, only the stability term, then it refers to the thermodynamic stability. So in order to differentiate the thermodynamic stability from that of kinetic stability, we have used some different terms. So if a complex is kinetically stable, then we call it as inert complex, and if a complex is kinetically unstable, then we call it as a labile complex. So first of all, this distinction was made by Henry Taube, and he was then professor at Stanford University, and he has worked tremendously in the field of coordination complexes, and he is winner of Nobel Prize. So, according to Henry Taube, the labile complexes are those in which ligands replace within a 1 minute and under the conditions of 25 सेंटीग्रेड टेम्परेचर एंड 0.1 मोलर रिएक्टेंट्स. सो वो कॉम्प्लेक्सेस जिनमें लिगेंड्स जो हैं वो 1 मिनट के अंदर 0.1 मोलर कंसनट्रेशन एंड एट 25 सेंटीग्रेड टेम्परेचर अगर वो लिगेंड रिप्लेसमेंट हो जाएगी तो दोज कॉम्प्लेक्सेस विल बी कॉल्ड एज लेबाइल और काइनेटिकली अनस्टेबल. और जिनमें ये रिप्लेसमेंट या सब्स्टिट्यूशन नहीं होगी उनको हम कहेंगे इनर्ट कॉम्प्लेक्सेस और काइनेटिकली स्टेबल कॉम्प्लेक्सेस. Moreover, there is no relationship or there is no linkage between the kinetic stability and thermodynamic stability. A complex may be thermodynamically stable, but it may be kinetically unstable. Similarly, a complex may be thermodynamically unstable, whereas it can be kinetically stable. So these two terms, thermodynamic stability and kinetic stability, are independent of each other. तो इसकी अगर हम एग्जांपल दें, सो दिस इज़ द एग्जांपल ऑफ निकल H2O6 कॉम्प्लेक्स, और इसमें जो है हम रिगन रिप्लेसमेंट करेंगे विद साइनाइड, तो वाटर जो है वो रिप्लेस हो जाएगा साइनाइड से. सो अगले स्टेप में अगर हम देखें कि ये एक कॉम्प्लेक्स है और ये बड़ा स्टेबल कॉम्प्लेक्स है, इट वाज स्टेबल, दैट्स वाई ये जो है इसमें वाटर की बहुत जल्दी जो है वो एक्सचेंज हो गई है. बट if we labeled an other cyanide with carbon 14 by using heavy isotope that is radioactive, तो फ़ौरन जो है ये साइनाइड जो है वो कॉम्प्लेक्स के अंदर आ जाएगा जो कि लेबल्ड है और रेडियो एक्टिविटी कॉम्प्लेक्स के अंदर आ जाएगी. दैट शोज दैट दिस कॉम्प्लेक्स इज़ थर्मोडायनामिकली स्टेबल था तो ये बना है, बट इसमें जो रिप्लेसमेंट है वो बहुत जल्दी हो गई है. सो इट मीन्स दिस वाज काइनेटिकली अनस्टेबल और इट वाज अ लेबाइल कॉम्प्लेक्स. नाउ क्वेश्चन इज़ कि यहाँ पर हमने साइनाइड जो है वो अंदर भी है, साइनाइड जो है वो बाहर भी है, तो व्हाई वी हैव यूज ओनली साइनाइड. द रीज़न इज़ दैट कि हमने टैगिंग की है, रेडियो एक्टिव कार्बन जो है वो लिया है. अगर हम साइनाइड की जगह पर कोई और लिगेंड यहाँ पर लेते तो उसकी नेचर चेंज हो जानी थी, तो वो उसमें हमें पता नहीं चलना था कि ये अब हम इसमें जो रिजल्ट आया है वो उसमें हम काइनेटिक स्टेबिलिटी डिस्कस करेंगे या थर्मोडायनामिक स्टेबिलिटी. सो इन ऑर्डर टू मेक द फैक्टर ऑफ थर्मोडायनामिक स्टेबिलिटी कॉन्स्टेंट, we have used the similar or identical nature of chemically identical nature of cyanide. तो उसमें हमने इसका हैवी आइसोटोप जो है वो C14 यूज़ किया है और उसकी जो है वो रिप्लेसमेंट हो गई है. सो दिस शोज दैट दिस कॉम्प्लेक्स इज़ थर्मोडायनामिकली स्टेबल बट इट वाज नॉट काइनेटिकली स्टेबल. सो इट वाज अ लेबाइल कॉम्प्लेक्स और इसी वजह से विद इन अ 1 मिनट जो है इसमें C14 साइनाइड की रिप्लेसमेंट जो है वो हो गई है. So in this particular example, we have seen that this particular complex is thermodynamically stable, but it was not kinetically stable, it was kinetically unstable, or it was a labile complex. Now हम next example देखते हैं जिसमें complex जो है वो thermodynamically तो unstable है, but इट इज़ काइनेटिकली स्टेबल. फॉर एग्जांपल ये देखें कि हमने यहाँ पर ये कोबाल्ट हेक्सामीन का कॉम्प्लेक्स है, एसिड के मौजूदगी में हम ये रिएक्शन करवाएंगे तो ये कॉम्प्लेक्स जो है वो डिकम्पोज होगा. द रीज़न इज़ दैट कि व्हेन वी ऐड एसिड सो इट डिजॉल्व्स थिंग्स। तो ये जो कॉम्प्लेक्स है, ये डीकम्पोजिशन इस कॉम्प्लेक्स की स्टार्ट हो जाएगी, और वी कैन सी say that this complex is thermodynamically unstable. So by taking in view these two examples, we conclude that if a complex is thermodynamically stable, then it does not mean it is kinetically stable. It may be kinetically stable or it may be kinetically unstable. Or in broader term, we can say that if a complex is thermodynamically stable, then it may be inert or it may be labile. So labileness and inertness has nothing to do with the thermodynamic stability of the complexes. So in terms of energy parameter, here we find the definitions of thermodynamic stability and kinetic stability. Okay, the stability of a complex depends on the difference in energy between the reactants and products, or the reaction energy, and this definition is talking about the thermodynamic stability. Whereas the lability or the kinetic stability or instability depends on the difference in energy between the compound and the activated complex. Activated complex is also called as the intermediate. If this activation energy is large, then the reaction will be slow, or it will be called as inert, or it will be called as kinetically stable reaction. So let's take here the example about which we are discussing. सो अगर आप देखें यहाँ पर दिस इज़ द एनर्जी ऑफ रिएक्टेंट्स एंड दिस इज़ द एनर्जी ऑफ प्रोडक्ट्स. सो रिएक्टेंट्स हैव टू बी कन्वर्टेड इनटू प्रोडक्ट्स बाय emitting excess amount of energy. So this reaction is exothermic in reaction in nature. So the formation of this product depends upon the energy difference between the reactants and the products. So if reactants energy is large, at in this case we say that it will convert it into products, and the products will be more stable because the products have been formed by the emission of the excess amount of energy. So now products are formed because they are more stable thermodynamically as compared to reactants. Whereas the difference between the reactants and the activated complex, which is present here, or the intermediate, so the difference in energy between the reactants and intermediates, this difference in energy controls the kinetic stability or instability of the complex. So if this difference is large, activation energy is large, the reaction will be slow, the complex will be kinetically stable, or it will be called as inert. However, if this activation energy is small, the activated complex will be formed easily, it will be formed quickly, so the complex will be called as kinetically unstable or a labile complex. Now for 6 coordinated coordination complexes, we can predict some order of or degree of reliability with which the complex will be labile or inert. So on the basis of which a classification scheme has been made. So first of all, we will classify the labile complexes, all those complexes in which the reactants react within a period of 1 minute at temperature of 25 centigrade and 0.1 molar concentration of reactants. So in case of coordination complexes, if the replacement of the ligand occurs in these conditions, so those complexes will be called as labile complexes. So all complexes in which the central net atom contains d electrons in Eg orbitals like dx square, y square and dg squares, then those complexes will be labile. Plus second, all those complexes which contains less than 3 d electrons, they will also be called as labile complexes. So in order to understand these complexes, let's have completely we have opened them in the form of their valence electronic configuration, and we will see how these electronic arrangements have been made possible and why the particular complex has been placed in a particular class of labile or inert complexes. So first example is this oxalate complex of gallium. So here is the complete situation. Outer charge on the complex is -3, so these are 3 molecules of oxalate. So each oxalate contains -2 charge, so 3 will contain -6 charge. So in order to balance the outer charge, we have placed +3 on gallium. So this is the valence electronic configuration of gallium, which is 3d10, 4s2 and 4p1. And when we remove these 3 electrons, so this is the valence electronic configuration of gallium +3, which is 3d10. So 10 electrons को कैसे place करेंगे? So this is the arrangement of Eg and T2G in case of octahedral geometry, and we have discussed it completely in crystal field theory that in octahedral geometry, Eg set of orbitals, which is T2G, which is dx square y square and dz square orbitals, they go upwards, they become higher in energy, whereas dxy, dyz and dxc, they become low in energy. Or in other words, we will see that Eg set of orbitals, they actually lie in the plane of the incoming ligands, and that is why these orbitals feel more repulsion with the orbitals or electrons of the metal, so they go high in energy, whereas these dxy, dyz and dxc feel less repulsion with the incoming ligand electrons, so they will feel less repulsion, so they are actually lying in between the space or the place from where the ligands are coming, so they are not directly in contact with the situation. So why these are labile? So all those complexes in which there are electrons in Eg set of orbitals, they will be labile. So in this case, although it is a D10 system, but it contains electrons in Eg, so this will be a labile complex. Now second example is cobalt hexamine. So it has +2 charge, ammonia is neutral, so in order to balance the outer charge, we will place +2. This is the electronic configuration of cobalt, its atomic number is 27. For 4s2 and 3d7, its electronic configuration. So in +2 form, these 2 electrons of s will be removed, so this is 3d7, which is the electronic configuration of cobalt +2. Now how these electrons will be placed in Eg and T2G? Because ammonia is intermediate between strong field and weak field ligands. In some cases we pair up electrons, and in some cases we don't pair up electrons because of intermediate strength of the ammonia. So here in this case it is considered as weak field ligand, and in weak field ligand there is less splitting between Eg and T2G, so electrons will fill in a pattern like first they will singly placed in all orbitals, and then the remaining 2 will be paired in downward. So although it contains electrons in Eg and these electrons come directly in the line of the ligand, so they have interaction with the ligand, so as a result of which this complex will also show labileness. Next example is this copper H2O6. Again it has charge of +2, water is neutral, so copper will be +2. This is the electronic configuration, valence electronic configuration of copper, which is 4s1 and 3d10. So we will remove 2 electrons, one from s and one from d, so this is its valence configuration of copper +2, and which is 3d9. Again we will place it like this because water is behaving like a weak field ligand, so this gap is not too much, so electrons will be go upwards and then the extra electrons will be pair up. So 9 electrons will be filled in this pattern like 1 2 3 4 5, and the remaining electrons will be pair up 6 7 8, and then 9th will be go upwards. So although it is a weak field ligand, the water is a weak field ligand, but as the electrons once again going into Eg set of orbitals, so this is also a labile complex. Next example is the nickel H2O6 +2. Again this is the valence electronic configuration of nickel. Nickel is in +2 form. This is the 3d8 configuration. So Again, water is a weak field ligand, so electrons will place like this pattern. So 5 electrons and remaining will be pair up. Again, this contain 2 electrons in Eg, so this will be labile. The reason is that because Eg comes directly in the path of the incoming ligand, so they will interact more, so there will be more chances of kinetic instability. So next example is this complex of iron. So in this complex, again water is attached and it is a weak field ligand. So valence electronic configuration of iron is 4s2 3d6 in plus 3 form. 2 electrons from S and 1 electron from D removes and 3d5 configuration, and it will be converted into this. Again, this contains 2 electrons in Eg, so it will be a labile complex. Similar case is with the titanium. This is its valence configuration and it is a D1 system. So here there is only a single electron and it will go into Tg, which is a lower, and it will never go into Eg. So here in this particular case there is no electron in Eg, but although no electron in Eg, but this complex is labile. Why? If we see here, so when there are less than 3 electrons in T2G, then all those complexes will be labile, because if we see here it is 1 electron and here there is no electron, so this will create a unsymmetrical situation. At one point there is more charge density and other point there is nothing, so this will create an unsymmetrical situation, and whenever there is an unsymmetrical situation, then that will lead to a labileness. So in this case, if we see a vanadium complex with the phenanthrolene, so this is the electronic configuration of vanadium, and in plus 3 form 2 electrons from S and 1 removes from 3 and D due configuration, and how these electrons will be filled. So here again T2G contain 2 electrons. This is also an unsymmetrical situation, so this will create a positive negative interaction. If you remember in chemistry, if there is a negatively charged present, so and attack will be from the positive species, or if the target is the positively charged, then the attack will be from the negative species. So this positive negative interaction leads to a chemical reaction. So here these two orbitals contain one electron, whereas this contain nothing. This create unsymmetrical situation or the unsymmetrical distribution of the charge density, so this will cause labileness of the complex. Here in this case, this is the complex of calcium, although it is not a D block element, but we are still studying this because of this complex. So this is the complex with EDTA and with single molecule. So only charge on the complex is -2. EDTA contains -4 charge. For we will place +2 on the calcium, so in order to balance the outermost charge on the complex. So this is the valence electronic configuration of calcium, which is 4s2 m3d0. And if we remove 2 electrons from S, then it contains only 3d0. So 0 means there is no electron, so this complex is also a labile. So D0 situation, D1 situation and D2 situation, these all lead to labile complexes, whereas all those complexes which contain their electrons in Eg set of orbitals, those will also be considered as labile complexes experimentally. Now if we take the examples of inert complexes, so here we take the complex of the chromium. So this is the situation, +3 on the overall. So water is neutral, so chromium will be +3. This is the electronic configuration of chromium, which is 4s1 3d5, and in order to remove 3 electrons, 1 will be removed from S and 2 will be removed from D. So this is a D3 situation. So again all complex electrons will go into T2G. There is no in Eg, so it will be a inert complex. So next example is this. Again overall charge on the complex is -3. Cyanide, 6 cyanides will cause -6, and in order to balance the outermost sphere charge, iron will be in +3 form. So this is the valence electronic configuration of iron, which is 4s2 3d6. So we remove 3 electrons, 2 from S, 1 from D. So this is a 3D5 system, and all electrons will be into T2G. Here, because cyanide is a strong field ligand, so it will create so much gap between Eg and T2G according to crystal field theory, that all electrons will be paired up here in T2G. There is no electron in Eg, so this will be a inert complex. All electrons are in T2G, and T2G electrons never come in the path of the incoming ligands, so this will be a inert complex. Here the third example is this cobalt hexanitrile complex. So it has charge of -3. 6 nitride will have -6 charge, so in order to balance the outermost charge, cobalt will be in +3 form. This is the electronic configuration of cobalt, which is 4s2 3d7, and we have to use +3 configuration. So 2 electrons will be removed from S, 1 will be removed from D, so it will be a 3d6 system. Again, nitrite ion is a strong field ligand, so all will be paired up in T2G, and there is no electron in Eg, so this will also lead to the inert complexes. So in inert complexes, we will see that if there is no electrons in Eg, then all the complexes will be inert, and if there are 3 electrons at least in T2G, then that complex will also be a inert complex. So here in this way we conclude this classification, which was based on the number of electrons in Eg and T2G set of orbitals. The other classification is based on the crystal field stabilization energy, and we shall discuss that in the next lecture. So I hope you all will understand this lecture. If you have any confusion, let me know in the comment section. I will reply immediately to the best of my knowledge. Okay, thank you. Allah Hafiz.